Welcome to This Explainer. Today we're embarking on a massive cosmic journey. We're going to break down the exact invisible force that is literally holding the entire universe together. Yep, we are talking about gravitation. Let's get right into it. Now, we all experience gravity, right? Every single time we drop something, there it is. But what is it really? And how does this exact same phenomenon dictate the motion of entire galaxies? As you'll see, from the absolute smallest particles all the way up to the largest supermassive black holes, it is all intricately connected. Our flight plan today is pretty straightforward. We'll hit 5 key areas. First, Newton's blueprint. Second, gravity on Earth. Third, energy and escape. Fourth, orbits. And finally, number 5, Einstein's cosmos. Starting right off with Section 1, the blueprint. Way back in 1665, Isaac Newton had a massive realization. He figured out that the exact same gravitational force pulling an apple down to the ground is actually the same force responsible for holding the moon in its orbit. It's a universal rule. He realized that every single particle attracts every other particle. Basically, this gravitational pull depends entirely on how much stuff, mass, the objects have, and it weakens by the square of the distance between them. Just to put that into perspective, if that whole myth about a falling apple inspiring Newton were completely true, the actual attraction between that apple and our incredibly massive Earth is only about 0.8 newtons. But here's the thing. Earth isn't just a tiny particle, is it? It's a huge, complex 3D object. So, to simplify dealing with complex objects like this, Newton mathematically proved what we call the shell theorem. Basically, you can think of Earth like a giant nest of uniform spherical shells. This means if you're standing outside of it, Earth attracts you as if all of its incredibly massive bulk were just a single, glowing point of mass perfectly concentrated right at its center. But, incredibly, the second part of the theorem says that if you were somehow hollowed out and inside a uniform shell of matter, the forces pulling you from all sides would perfectly cancel each other out. You'd experience exactly zero net gravitational force. Okay, so what happens when multiple objects are interacting at the same time? Well, that's where we bring in the principle of superposition. It's a bit like a giant puzzle. You can't just mash all the numbers together at once. Instead, you have to calculate the individual gravitational force vectors one by one for every single pair of particles involved. Once you have all those individual forces, you add them all up, carefully accounting for both their magnitude and their direction, of course, and that finally gives you the true net pull on any given object. Moving on to Section 2. The earthly experience. Now, you're probably super familiar with using the standard g of 9.8 meters per second squared for an object in freefall. We use it all the time. But the actual theoretical gravitational acceleration, what physicists refer to as a sub g, is slightly different. See, this a sub g value is calculated by assuming Earth is a perfect, uniform, completely non-rotating sphere. And, well, spoiler alert, it definitely is not. The reasons why these two numbers differ are actually super fascinating. First off, Earth's density isn't uniform at all. It varies wildly from the crust all the way down to the core. Second, Earth isn't a perfect sphere. It's an ellipsoid. It literally bulges out at the equator, meaning you're physically further away from the center of the Earth down there than you are at the poles. And finally, Earth is rotating. Because it spins, if you have a crate sitting on a scale at the equator, that crate is actually traveling in a giant circle. That motion requires centripetal acceleration, which slightly counteracts the inward pull of gravity. So, a scale at the equator will actually read a slightly lower weight than that exact same scale would at the North Pole. Crazy, right? So, what if you actually go underground? There's this classic sci-fi trope about digging a tunnel straight through the Earth from pole to pole. If you jumped into it and fell through, the gravitational force pulling you down wouldn't just keep increasing endlessly. Actually, because of that shell theorem we just talked about, the outer layers of the Earth that you passed through would completely cancel each other out. The force pulling you down would decrease linearly as you approach the center, eventually hitting exactly zero right at the Earth's core. You'd just be floating there. All right, let's jump into Section 3, Energy and Escaping Gravity. Think about a bungee jumper. As they fall, the physical separation between them and the Earth is rapidly decreasing. What's happening energetically is that the entire system's gravitational potential energy is rapidly transferring into thrilling, fast-paced kinetic energy as they speed up toward the ground. It's an awesome, real-world energy exchange. Now, in physics, we actually define this potential energy as exactly zero when two objects are infinitely far apart from each other. Because gravity is always an attractive pull, the system essentially does negative work to bring those masses closer together. So counterintuitively, this means the gravitational potential energy becomes progressively more negative the closer two objects get to one another in space. Building on that, if a rocket, or really any object at all, wants to permanently escape a planet's gravitational pull and reach that infinite distance where potential energy hits zero, it absolutely must hit a specific velocity threshold. We call this the escape speed. It's a delicate piece of cosmic math that depends entirely on just two things: the mass of the planet you're leaving and your starting radius from its center.
Next up is Section 4, Planetary Motion and Satellites.
To truly understand planetary motion, we have to look at Kepler's three laws. First, the law of orbits tells us that planets move in ellipses around the sun. Then, the law of areas ensures they sweep out equal areas in equal times, which basically means they speed up like crazy when they swing in closer to the massive body. And third, the law of periods, which states that the square of a planet's orbital period is directly proportional to the cube of its orbital radius. Furthermore, when we look at orbital energy, a satellite's kinetic and potential energies perfectly balance each other out. This elegant balance is what keeps it locked in a stable circular or elliptical orbit, preventing it from either flying off into deep space or crashing back down to the surface.
Finally, let's zoom way out for Section 5, Einstein's curved spacetime.
When we look out at massive, mind-bending structures like the Andromeda Galaxy, which is located a staggering 2.3 million light-years away from us, or at the supermassive black holes lurking at the centers of galaxies, Newtonian physics just doesn't give us the whole story. For instance, the black hole at the center of our Milky Way has a mass of about 3.7 million suns. The gravity there is so overwhelmingly intense that even light itself cannot escape its grip. So Albert Einstein realized something truly profound that started a total revolution in physics. Imagine a physicist locked in a closed, windowless box that is accelerating through deep, empty space at 9.8 meters per second squared. Einstein postulated that this physicist would feel the exact same downward push and read the exact same weight on a scale as someone simply resting on the surface of the Earth. This became known as the principle of equivalence. It states that gravitation and acceleration are fundamentally the exact same thing. And this single thought experiment led to an absolutely groundbreaking realization. Gravity isn't an invisible force pulling objects together at all. Actually, scratch that. It's more like massive objects physically warp the actual fabric of space-time around them. So objects aren't being pulled by a mysterious force, they're literally just following the straightest possible paths along a newly curved geometry. It completely flipped our understanding of the universe on its head. Incredibly, we don't just have to imagine this. We can actually visually prove this geometry is real. Through a phenomenon called gravitational lensing, massive structures warp space so severely that they literally bend the path of light itself. When a massive galaxy sits directly between us and a distant, bright quasar, the light from that quasar bends around the galaxy, blending together to form a glowing, luminous arc. We call this beautiful structure an Einstein ring. Einstein's sudden realization while sitting at a desk in the patent office redefined our entire universe. It proved that what we perceive as the heavy, downward pull of gravity is actually just our journey, our free fall along the beautifully curved landscape of space and time. So as you ponder the massive, mysterious structures of our universe today, ask yourself, are we truly being pulled down by invisible threads of force? Or are we simply sliding down the beautifully curved contours of space-time itself? It's a lot to think about. Thanks so much for joining me on this explainer, and definitely keep exploring.